Okay, so let's break into chapter 4. Um, Chapter 4 is really going to come down to looking at electrons. In fact, electrons are responsible pretty much all of the chemistry. Okay, so we talked about protons and neutrons. We talked about the atom and how it's structured, and it's great. The middle of the atom, the nucleus of the atom, is where all the mass is. The electrons are around the outside, but the electrons are almost exclusively responsible for all of the chemistry that we're going to talk about. Okay, so mass is important. We're going to talk about why that's important because different things weigh different amounts, and that's going to be part of the conversation. But really, the electrons are what kind of control everything. So let's briefly talk about how electrons work and more of like how light works. So if you have a continuous source, a continuum source like this, okay, so this is really what that is there is that is called, well, that's white light. Okay, so white light, if you've ever looked through a prism, you see that generally how we get this stuff to break is if I take white light and I send it through a prism, um, what you end up with is you end up with a continuous, you see all of the colors of a rainbow. In fact, that's what you see when you see a rainbow. It's just that the light has been bent so you can see all the different portions of it. Red, orange, yellow, green, indigo, blue, violet. So uh, you see every single color in the rainbow. Okay, so that is a continuous source of energy. Well, a scientist at some point said, okay, uninterrupted, this is what you see. You see this continuous source of energy. But if you take a gas like hydrogen, okay, and I just take a source of hydrogen and I put it in the way of that continuous source, what happens? Well, it turns out that when you put that hydrogen gas in the way, some of that light actually gets consumed or it gets absorbed. So here we see that there are a bunch of lines, these black lines that appear, and we're not sure why, at least we're not sure why right now. So what happens is this light right here is light that was absorbed. You can see all these little black lines here. All of this light was absorbed. Well, the question is, what was it absorbed by? The only possibility is hydrogen, right? Because over here in the left, we didn't see this loss of light, right? All of that, we see all the entire rainbow. Here, we're missing little bits of the rainbow. That's because the light was absorbed by the hydrogen. Well, that's really interesting. You would think that the hydrogen would either A, not absorb anything, or it would absorb a bigger portion of this. So why do they only absorb these little bits of light? And even more interesting to this is if the hydrogen is absorbing this light, well, we can't lose energy. It's got to go somewhere. And so actually, if we look off in another direction, you can see that that light is emitted by hydrogen. Okay. And what you'll notice is down here, I have this little red color that's missing. Well, this red color is right here. Again, that's from the other angle of hydrogen. So the hydrogen absorbed that light and then releases it elsewhere. Okay, you see that we're missing this like greenish, bluish color, green here. Well, it's right up here. And notice that we have this blue that's missing here. We have two actually, blue that's missing here. And there's another blue here, another blue here. Okay, so the hydrogen absorbs some light and it essentially releases it. This is called, and you don't need to know this, but this is called the quantization of energy. Especially what ultimately happens is hydrogen absorbs some very specific colors of light, and that's it. So that's pretty amazing stuff considering considering we see these little lines and these little lines only. Well, it turns out that this happens, and if we can actually see this, we can observe this as one of the experiments that we actually do in the general chemistry class, is we see that this hydrogen, and if we take hydrogen and we excite it, we do see those colors and we can assign energy associated with those. So we can say, okay, the red is at 656 nanometers, and it turns out we can just apply some light to it, some energy to it. So there is an energy associated with those little bits of light that are missing, or those little bits of energy that we see. You don't need to know these equations down here. It's just very interesting to know that we can see these things. So ultimately, what's important from here? What we see is an element, in this case hydrogen, is absorbing very specific sources of light. And now we want to know why. Well, it turns out that we have electrons. We talked about having a nucleus. We're going to ignore the nucleus for now. It turns out that electrons tend to hang out in orbitals. Okay, so this is an orbital around the nucleus. And it's not just one. Okay, so the first one actually has 2. The next orbit is going to have 8. And we're going to get over how we figure all this out. And actually, you don't really even need to know this, but each of these orbitals contains a bunch of electrons. And those things are what responsible. The electrons are not, and this is where the quantization part comes. This is why we see specific lines. The electrons are not allowed in between. This is a forbidden region. Electrons are not allowed to be there. Electrons are so precise that they can be in this orbital, or this orbital, or this orbital, or even further out. There's more out here, but they're limited to those locations. Okay. Ultimately, what this means is electrons, you don't need to know anything about this other than electrons are limited to specific locations. Or really, I should just say orbitals. And this is quantization of energy. If you get on the ground floor, or the first floor, okay, at any high rise, at any hospital, anything like that, you can go to floor 2, 3, 4, 5, 6, 7. You can't stop in between. Electrons are the same way. If they're on the first floor, they can jump up to the second, the third, the fourth, but they can't go to floor 1.5. Okay, they're always limited to those specific locations. And that brings us to the idea of where electrons are allowed to be. This looks super complicated, and it's really not. This is how electrons fill. And you don't really need to worry about this because we're going to go through this all together. But over here, let me just explain what it looks like. Over here, we have energy. That's what the E stands for. And as I go up, I'm seeing more and more energy, which means that something way up here has a ton of energy versus this very first one, which has very little energy. Okay. Each of these little dashes is known as an orbital. Okay, so this right here is an orbital. Each orbital can hold 2 electrons. Okay, so, and by the way, there are 2 electrons that it can hold. We have a choice. An electron can be known as spin up, so an up arrow, or it can be known as spin down. So every single orbital is going to look like that diagram. 1 spin up, 1 spin down. Okay, that's it. That's all you're going to have ever. By the way, I will shorten them and they'll look like this. That spin up, that spin down. Okay, so just half of an arrow. Those 2 things are absolutely the same. And you could totally write spin down first. So you could do this and then that. None of that really matters, but you can never have them have both the same spin. And we're going to talk about that in just a moment. Okay. All right. So if you were putting electrons, if you were going to fill this up with electrons, where do your electrons go first? And the answer is you always want to put things in the lowest energy state possible. So I would put my first 2 electrons there. And then I see that this one's next, and I would put the next electrons there. The next electron is going to go in the 2p. And actually, we prefer to put them in their own orbitals before we match them up, and so on and so forth. Okay, so we are going to fill up based on where we're allowed to put electrons. and we're always going to go with the lowest energy first. Oh, see, that was wrong. I should fill them up individually first, and so on and so forth. You really never need to know the order because I'm going to explain how you determine the order, but that's the idea. So we have three principles associated with filling up, basically filling up orbitals. So the Aufbau principle is our first one, and we've already talked about it. Lowest energy fills first. So the lowest energy fills first. So if I have 1s, 2s, and I was putting 2 electrons in, that is okay. And we're going to talk about all the notation. That is not okay. Okay, so that does not happen. So we always want to fill up the lowest energy first. The Aufbau principle, the filling up principle, and we're going to actually have a much simpler way to do this. Next up, the Pauli exclusion principle. And if you're doing this correctly, you never have to think about these things. They have been given names, and I'm going to give them names to you. The next one is the Pauli exclusion principle. Basically, Pauli exclusion principle is what I've already said, which is basically say one spin up, electrons cannot have same spin in an orbital. So if I'm looking at a orbital, we'll call this the 1s again. There is one way that this can happen. That is okay. This is absolutely not okay. So you can't have them being in the same direction. You can't have 2 electrons facing in the same direction. That is not okay. Okay. Oh, by the way, I do want to go back to the first one, the Aufbau principle. This we would call the ground state. This is like a low energy state. That's what we expect. This one right here is going to be called the excited state. It's okay to put an electron in a higher orbital, but it's not going to be the most stable version. Okay, so we're always going to do ground state electrons where they're going to be in the lowest orbital. The excited state is if something is just way up there. Okay, so always look out for that. We're always doing ground state. We're always doing the simplest version of it. The Aufbau principle is going to predict the ground state. Okay. All right, the last one is Hund's rule. When we get to multiple orbitals, so if I'm looking at, let's say, the 2p, we want, the Hund's rule is simply says that we want to fill orbitals of same energy before pairing. Okay, so in this case, if I put 3 electrons in, I would put the first 3 there, and then I am forced to pair. Okay, so this is correct, right? So that's what we're looking for. I do not want to fill it like this. That is not what we're looking for. We want to make sure that we do individual electrons in each of the orbitals before we pair. Ultimately, this is not really going to matter to you all that much, but that's the idea, okay? All right, good. So there is a shell, subshell, orbital filling of electrons, and we're just going to get used to it, okay? So I'm going to show you how to come up with this order. We know that we would always fill, and we've already done this, according to the Aufbau principle. That is the lowest energy electron. I'm going to put it there, and I'm going to pair it up. The next set of electrons is going to go there. The next electron I'm going to put in the 2p. So now the question is, where do I put it? Do I pair that electron, or do I put it in the other 2p? I would put it here according to Hund's rule. Hund's rule says I'm going to fill up those before I start to pair up electrons. Then the 3s and then the 3p. So this is the process by which we're going to fill these things up. Okay. All right, good. All right, moving on. So a couple of things, again, if I'm filling this thing up, I should say this right here, this is wrong. This violates Hund's rule. Okay. This one right here, this is not wrong. Okay, this is okay. But what this is this is an excited state, not ground. So for our purposes, this violates the Aufbau principle, AUF, AUB. Oh, Auf, BAU, sorry. So that violates the Aufbau principle. All right. And then the last one, we'll do this one really quick. That one right there is wrong because I can't have two electrons with the same state, with the same spin. Okay, so that one is going to be, yeah, so that violates, I can't remember the name right now, the Pauli exclusion principle. Okay, so those are the, so what this comes down to is just simply fill the lowest energy first, always keep them unpaired before you start pairing them, like fill the 2p before you fill anything else, and don't put spins with the same spin in one orbital. Okay, all right, great. And so we're going to take a look at actually doing this stuff next, but this is a good place to stop.